Okay. Before we start going through the slides, are there any questions that any of you have at this point? No questions? Okay, then let me share the slides. Just a second. Oh, here we go. This one. Okay, so you should see the slides OCN201 Module 4 upwelling. You see this? Yes? Okay, nobody disagrees. Okay. Okay, so again, OCN201 Module 4 review. First of all, our exam is this Friday. That's Friday, February 28th. It's at 10:30 and 12:30, 10:30 a.m., 12:30 p.m. And it's in the Biomed building. Again, please, last time there was some confusion about the location. The exam is in the Biomed building B103. That's the same location that the Module 3 exam was being held, same time. Okay, so in Module 4, we went through 4 different topics. It was upwelling, including El Nino, mesoscale variability or mesoscale eddies, waves, and tides. So as in years past, what I have here is a concatenated version of all the slides that were included in all of the presentations that you have reviewed online. All of the material should be interesting to you, and I would ask you to review all of it. However, as in years past, we have gone through these slides and marked with stars slides or content that's particularly interesting and particularly important. And so if you're pressed for time, you might want to start with the start slides and then review the rest of the material. Any questions so far? Not sure where switching my. I can't even see the. Oh, come on. Chat. Okay, no chat. Okay, good. Okay, so we had 4 sections, as I said: upwelling, mesoscale eddies, waves, and the tides. So let's just go through them. The upwelling, the most important thing is really the occurrence of upwelling both at the equator and at the eastern coasts of the basin, and that comes about because the winds, the Ekman transports, according to associated with winds, are on the northern hemisphere to the right of the winds, and the southern hemisphere they are to the left of the winds. So if you apply that first to a coast, as you see in this picture, in this grainy picture of the coast of South America, for the South America, you have prevailing winds that are equatorward. On the southern hemisphere, these equatorward winds will be associated with the transport to the left. That means towards the west. And that means offshore. And so the Ekman transport will transport water offshore, and this water will be replaced by waters from below. That it will be colder and nutrient-rich, which is one of the reasons that the eastern boundary currents, these upwelling regions, are associated with both cold temperatures. If you've been to California, you know that, California, Oregon, and also very, very high productivity. Now on the equator, similar thing happens. Now we have the equatorial Pacific is under the influence of the southeast trades, the southern hemisphere trades. They reach across the geographic equator to the meteorological equator, to the tropical convergence zone. So we have overall the winds that blowing from the east to the west. We have easterlies blowing along the equator. On the northern hemisphere, these easterlies will produce an Ekman transport towards the north, towards the right, towards the north, the right of the winds, towards the north. And on the southern hemisphere, these winds will produce an Ekman transport to the left of it, which is to the south. And so the Ekman transport will be divergent on the equatorial region and will, similar to the coast, it will bring back waters from below the surface to the surface. If the thermocline is shallow enough, then it will draw cold water to the surface, and it will also draw nutrient-rich waters to the surface if this upwelling can reach the thermocline waters that are both cooler and higher in nutrients. And that's what you see here in this picture. You see this greenish colors, these darker colors, these are colder temperatures. When you see them, how they are right on the equator, you have this tongue of cooler waters that are associated with equatorial upwelling. Any questions? Okay. So then this equatorial upwelling is tightly related to El Nino. If we go to El Nino, we have to first understand the neutral or the typical, the average state in the tropical Pacific. In the tropical Pacific, we have winds blowing from the east to the west. We have the easterly winds that we just mentioned in terms of equatorial upwelling. And what they will do, these easterly winds blowing along the equator, they will pile up the surface layer waters, the warm surface layer waters in the Western Pacific. And so what you see in this picture, you see an indication of the winds and associated with them the Walker circulation, this east-west overturning circulation that we have, the surface expression of the Walker circulation, again are the trade winds, and they move the water towards the western region. And as a result of that, you see in this lower picture up here, you see the depiction of a section along the equator, with depth being the vertical axis and horizontal being simply longitude along the equator. And this piling up of warm waters in the Western Pacific is associated with the depression or deepening of the thermocline in the Western Pacific and the shallowing of the thermocline in the Eastern Pacific. The shallowing of the thermocline in the Eastern Pacific, of course, is consistent with the upwelling discussions that we just had. And overall, we have this sort of situation that we have the trade winds deepen the thermocline in the west and shallowed in the east. Associated with that is cooler sea surface temperatures in the east and warm sea surface temperatures in the west. Now, the warm sea surface temperatures in the west, they anchor the centers of deep convection in the Western Pacific, the strong precipitation regions in the Western Pacific. And in these precipitation regions, we have all the latent heat flux or the evaporation heat flux that's picked up by the trade winds, that's being released in the atmosphere, and that forces this entire system, this overturning circulation. It forces the air up and maintains the trade winds. So this is the neutral condition. And you see already this is a coupled system. It involves both an interaction of the ocean and the atmosphere, and elements are the trade winds piling up water or causing equatorial upwelling in the east, piling up of water in the west. This is associated with the equatorial thermocline, which brings the thermocline to shallow levels in the east, maintaining this low sea surface temperatures, and these warm waters are anchoring the center of deep convection and maintaining the trade wind. So this is overall a feedback loop between the equatorial ocean and the equatorial atmosphere. Now, this is the neutral situation. Now, if we go to an El Nino, let's see what we have here. During an El Nino phase, we see that system changes quite a bit. You notice that we have, sorry, if you just go a few slides back, let's just stay with this picture actually. Now, if you can think of ourselves, I think we perturb the system and they say, okay, now let's make the trade winds a little bit stronger for whatever reason. We just make the trade winds a little bit stronger. Then that would pile up more water in the east and bring the thermocline closer to the surface in the west, and thereby making stronger the east-west temperature gradient, making the waters in the east even cooler. So that will then increase the trade winds, pile up even more water in the west, bring the thermocline even shallower, and spin up the trade winds again. So there's a positive feedback in the system built in that will have an increase in the trade winds, will make the system go into a state where we have even colder water in the west and warmer water in the east and a stronger trade winds. Or conversely, if we think of the situation that we decrease the trade winds, if we decrease the trade winds, then we would reduce the upwelling in the east. We will reduce the tendency to accumulate water in the west. In fact, some of this water in the west will flush back towards the east, and that will depress the thermocline and make the waters in the east even warmer, further weakening the trade winds. So there's an instability in the system that is underlying the El Nino situation and the La Nina situation. So if we go to El Nino situation, what happens? As we just said, we had weaker trade winds during a linear situation. So we have the thermocline slope is relaxed, it's steeper throughout, has very little slope to it. As a result, we have anomalously warm situation in the Eastern Pacific, cool situation in the Western Pacific. And with these changes in sea surface temperatures, the centers of deep convection move from the Western Pacific to the Central Pacific, and we have a modulation of the Walker circulation overall. So this is what's underlying El Nino, this sort of instability. As you can see, this is really a rearrangement of the tropical coupled ocean atmosphere climate that we have during an El Nino. During a La Nina, exactly the opposite happens, that we have, as we discussed in the earlier parts of this discussion, we have stronger trade winds, which makes piles up more water in the west, brings the thermocline to shallower depths in the east, makes the east-west temperature gradient larger, and therefore increases the centers of deep convection and makes the trade winds even larger and makes it even stronger. So if there's two situations, there are processes, of course, in the coupled system that stops this feedback, which we haven't discussed. But these sort of feedbacks are underlying the evolution of both El Nino and La Nina. Now, if we think of the El Nino, La Nina identifying events, you just have to see here, this is a nice picture. This is a depiction of surface temperature, absolute surface temperature, and the anomalies, the deviation from normal seasonal cycle, as a function of longitude and time, where time is running from the top down. And this is along the equator from true south to true north. That you see here, basically the same thing as temperature, the full temperature and the anomalies. You see very nicely this evolution, the development of very warm sea surface temperatures in the east associated with the El Nino conditions in this period. This is 1996, 1997 El Nino condition. Here we have the 2015, 2016 El Nino. We also see the opposite happens during La Ninas when we have anomalously cold sea surface temperatures in the east. You see this here even in the full temperature. You see it very clearly, this evolution of this cold sea surface temperatures with the La Nina of 1988, 1989. Okay, so these El Nino variations, as I said, they rearrange the tropical system. They rearrange the centers of deep convection where they're located. And that is generating processes in the atmosphere that communicate the changes in the tropical Pacific to around the globe. And in particular, what they do is these changes in the equatorial Pacific, they generate very low frequency waves in the atmosphere, and these waves rearrange or affect the position of the jet stream. This overall communication of the changes in along the equator, centers of the convection, to changes around the world, this is called teleconnections. And these teleconnections are underlying, again, changes in the jet stream, and you see that in North America, we have overall the jet stream dips into the Pacific and it moves the whole storm track to the south. And as a result of it, we have over North America, we have warmer conditions in the northern half of North America, colder conditions in the southern half, and you have much wetter conditions in the southwest. Now, it's not just that conditions are affected over North America, but there are repercussions of El Nino everywhere in the world, and these are indicated by this picture. They're seasonally modulated, so in the boreal winter, in the northern hemisphere winter, we have these conditions. Again, you see these colors nicely. You have during El Nino, we have warmer conditions here, cooler conditions there. It's also wetter here and drier here. We have the changes in North America that we just mentioned in terms of wet and dry, warmer and cooler and wetter down here. But there are also changes everywhere else in the world, including in Brazil, South America, Australia, South Africa, and the like. In particular, in summer, in the Northern Hemisphere summer, one important impact is over India, where the monsoon is affected by El Nino. During El Nino, we have a drier condition during the monsoon. Of course, that affects enormous number of people in the monsoon regions in the Southeast Asia. Okay, any questions for El Nino so far? Okay, locally, El Nino has a number of impacts on Hawaii. During El Nino, we have a higher likelihood of hurricanes. That's because waters around Hawaii are somewhat warmer and the trade wind shear is reduced. Warmer sea surface temperatures are conducive to the development of hurricanes. Strong trade wind shears, meaning the change in wind speed as you go up in the atmosphere through the trade wind region from the surface going aloft. If this vertical change in the winds are stronger, that will diminish the likelihood that you get a hurricane, so will dampen the hurricanes. And we have here during this September 2015, during El Nino, we have actually this famous picture of being 4 tropical cyclones in various stages of their development in the tropical Pacific. We're very lucky that nothing hit us, but during El Ninos, there's a higher likelihood of encountering hurricanes in our home state. We also see overall the impacts of high weather. It's not just hurricanes, but you see overall that we have rainfall. We have more rain in the beginning of the season and then rapidly less. So if you have a drier wet season, the wet season is in the second half or the early part of the year. So we have overall a drier wet season in Hawaii. The trade winds are weaker. Sometimes they even reverse. Sea level is up. Overall, the ocean is much warmer. Again, I cited both of these, the trade winds and the ocean conditions, as being responsible of an increased risk in tropical cyclones and hurricanes. Okay, that's what you just had. Any questions regarding El Nino impacts? Okay, so in the second part of okay, this is still 5. I should check this, change it to 4. Right. So in the second part of this module, we looked at the mesoscale circulation. So we are now moving away from the mean conditions that we have concerned ourselves so far in terms of the mean ocean circulation. But we look at these swirls and eddies and changes in fronts that are associated with the ocean mesoscale. This is spatial scales of about 550 kilometers to 500 kilometers. The variations that we look at have these spatial scales and time scales of, let's say, 10 days to 3 months. The important thing is these mesoscale eddies. So eddies are these circular features of the ocean circulation and pressure. They are in venially and geostrophic balance. So what we learned about geostrophy applies to these eddies. So if you have an overall eddy that's associated with a low pressure at the surface, then it is associated with cyclonic circulation, meaning in the northern hemisphere, it's a situation in the circulation in the counterclockwise direction. These, as we show in the next slide, these cyclonic eddies are typically associated with the cold core. So surface temperature and temperatures in the thermocline, in the surface waters below the surface directly, in the waters below the surface directly, these are normally cool, the temperatures here. And as I said, it's counterclockwise in the northern hemisphere. They're clockwise in the southern hemisphere. So in the southern hemisphere, there's still low sea surface height, but they turn clockwise in the southern hemisphere to low. Still considered a cyclone. The opposite situation is if you have a high sea surface temperature, then you have an anticyclonic circulation associated with this. The anticyclonic circulation is clockwise in the northern hemisphere, but counterclockwise in the southern hemisphere. And these features, these eddies, the anticyclonic eddies are associated with the deepening of the thermocline and warmer temperatures at the surface in the thermocline. That you can see that very nicely here in this plot. And this is cyclonic and anticyclonic eddies. So this is a cut through an eddy. You see, first of all, here depiction of the eddy as shown for the northern hemisphere with the circulation indicated. Counterclockwise circulation in the northern hemisphere associated with the cyclonic eddy. And you see, if you now make a cut through this eddy, you see these colder waters indicated by this bluer, the darker colors here. They are brought back to the surface, closer to the surface. Associated with this upwelling or this shallower thermocline in the eddies, you have typically higher biological productivity because the deeper water has more nutrients and they are now closer to the surface and being accessible in euphotic zone for the biological activities. Anticyclonic eddy, opposite situation. Now in the northern hemisphere. Oops, let's make this a little bit bigger. Now do I change this size of these things? Don't show again. Make this a little bit bigger. Okay, anticyclonic eddies in the northern hemisphere, they're clockwise circulation. Now here you see that the thermocline is depressed, it's lower. As a result of this, the colder waters are further away from the surface, and also the nutrient-rich waters are further away from the surface. So they are associated with lower biological productivity and typically maybe a little bit warmer sea surface temperatures. Okay, by the way, I have posted these slides on Laulima, including these stars for review. Yeah, that's it. So you can view the entire slides. These are all the slides of all the movie loops that you've witnessed, you've shown, you've seen so far, and they have been all concatenated into one large PDF. You know, these eddies, they are not distributed evenly throughout the ocean, but they occur everywhere in the ocean, but the amplitude and the strength is changing from place to place. Now, since they have a surface height signature, as we just said, they have a high or low pressure, low pressure being cyclonic, high pressure being anticyclones, we see that if you look simply at its standard deviation, so the variations of the pressure around the mean, then we see these areas of very high sea surface height variations, which are associated with high eddy activity in the western boundary currents of the Kuroshio, of the Gulf Stream, of the Agulhas, in the South Africa. This is in Malvinas Current or East Brazil Current, Malvinas Current or Falkland Currents, depending where you are from. Or you see that here in the East Austral Current. So these western boundary currents are associated with enhanced variability of eddies. Now, in Hawaii as well, you see we have in the lee of Hawaii, we have also enhanced eddy activities, and these eddies are associated with this funneling of the trade winds through the gaps between the islands. This generates wind stress curl, as we discussed, and generates an undulations, upwelling or downwelling, depending on where you're on the islands, in the lee of the islands. These eddies then subsequently propagate from the Hawaiian Islands. Oops, let's go. Where was this here? Propagate from the Hawaiian Islands to the west. The important thing is that these eddies are caused by the winds funneling through the gap between the islands. The trade winds funneling through the gap between the islands. Questions regarding this so far, mesoscale eddies? Okay. Now, western boundary current eddies, we just mentioned, western boundary current are an area of very strong variability, of eddy variability. We saw that in this depiction of the standard deviation or variance of sea surface height from satellites that I showed you just a few slides ago. They are associated with the western boundary current itself, shown very nicely here in terms of the Gulf Stream. As it undulates, these very strong currents are unstable and they wiggle around, and they can actually pinch off eddies. So this is a schematic of this pinching of eddies. So if this is the Gulf Stream, we have cooler waters to the north, warmer waters to the south, and the jet is unstable, makes these undulations, and the undulations can become so large that they pinch off, so that the eddy reconnects, or the current reconnects here and produces an isolated eddies. If these pinch-offs are going to the south, into the warmer waters to the south of the Gulf Stream, they trap cold water, and they are associated with the circulation that's a cyclonic circulation. Whereas if we go on the warm side, same sort of process, but we have now an undulation or meander of the Gulf Stream that pinches off into an eddy, but it pinches off towards the northern, the cooler side. It will trap warm waters, and associated with this will be an anticyclonic eddy. You see it very nicely here in the pictures. This is just a snapshot of the Gulf Stream. You see the Gulf Stream here as this warm ribbon, warm being this warm temperatures, and you see this nice warm core eddies being pinched off to the north of the Gulf Stream. South of the Gulf Stream is not quite as obvious in the sea surface temperature, but the same process happens to both sides on the equator. But again, producing warm core eddies or anticyclones on the northern part, on the cool side of the Gulf Stream, and cyclones, cool eddies on the southern part, on the warm side of the Gulf Stream. Now, another example, of course, of this eddy formation is the loop currents themselves. This is loop current here, happens in the Gulf of Mexico. You're supposed to call it Gulf of America now, but let's just stick with Gulf of Mexico. This is in the Gulf of Mexico. We have the Gulf Stream coming through the Strait, Yucatan Peninsula, between this strait between Yucatan and Cuba, entering the Gulf and making sort of a loop before it exits the Gulf between in the Florida Strait between Cuba and Florida, and going along its way in the Atlantic. So this process again can pinch off eddies. You can see already pinches of eddies. The warm waters are a little bit warmer on this side than in the Gulf, and so these trap warm waters, and they have a circulation that is clockwise. So these are anticyclones. Once they pinch off, they propagate to the west. Very important because it also impacts both the ocean circulation, but also a possibility of hurricanes here in the Gulf of Mexico. Okay, so that's all I have for the ocean mesoscale in the reviews. Questions? Okay. So then the second part, or actually the third part of the discussions that we had here in Module 4 was surface waves. Again, that should be 4. And so surface waves, there's actually quite a few videos that you should view. So there are a number of important things that we have to consider when we look at waves is what is the disturbing force, what is the restoring force, and what causes the waves. And in general, for the surface gravity waves that are the main focus here, the restoring force is gravity. So basically, just like a spring, if you bring a spring down, then the spring will be stronger. The restoring force in this case will be actually for this thing will be restoring force will be both the strength of the spring and gravity. If you push it up, then gravity will be stronger than the force of the spring. It will fall down and overshoot and starts to oscillate. So here, for the spring, it's a combination of the spring itself and gravity. For the ocean, the restoring forces in general, they tend to flatten or restore the perturbation back to its original position. Inertia in the system can cause it to overshoot and generate an oscillation. Right, and so we have a number of processes, a number of waves that we consider in the waves, some capillary waves where the disturbing force is usually wind, and the restoring force is the cohesion of water molecules that causes surface tension. Make very short waves, just in the centimeter range, to wind waves, seiches, and tsunamis. They are distinguished both by their wavelengths and the way they are generated. Wind waves, as the name says, are generated by the winds. The restoring force is gravity. Tsunamis are generated by faulting movements of the seafloor, volcanic eruptions, or landslides. Again, their restoring force is gravity. They're typically associated with very different wavelengths, as we discuss in a minute. Wind waves are 60 to 150 meters, something like this. The tsunamis are very long, hundreds of kilometer wavelengths. And of course, tides. Again, the restoring force is gravity, as we see, but this is now the modulation of gravity by the Earth-Moon or Earth-Moon-Sun system. And so they're generated by these modulations of gravity, and again, restored also by gravity. Okay. So for the wind waves, the winds are generated by the wind waves are generated by the winds. Again, as we just said. 3 factors affect the growth of these winds. Oh, come on. 3 factors affect the growth of these winds. Let's see here. This is the one. All right, the wind strength, the wind duration, and the fetch. Wind strength is obviously how strong the wind is blowing. Wind duration, how long these strong winds are lasting. And the fetch is a spatial domain over which the winds are strong and last for quite a while. Right? So short winds that blow over short distance and short duration will not generate large waves, but however, if winds are strong and they blow for a number of days and over 1,000 kilometers, a large fetch, they will generate these sort of fully developed seas that you see here. So let me just say here, so the strong winds that blow over long durations, over long distances will continually build larger and larger waves. And this irregular peak chaotic waves that we see right in the generating region, that's called the sea. And you see that here depicted how this wave generation actually goes. You start with capillary waves. The winds blow over the ocean surface and generate capillary waves that causes feedback that these waves will grow in both in amplitude, but also in wavelength. And so they will become longer wavelengths from this 1.73 centimeters into a gravity wave regime of tens of meters to hundreds of meters, and they will grow in size. As they become higher and higher, their steepness will increase. In particular here, the height is really the steepness of the waves is a ratio of the wave amplitude towards wavelength. If that ratio exceeds a ratio of 1/7, then the waves break and form whitecaps. This is one of the ways by which we stop the growth of the waves. Again, the winds they generate the waves and make the wave field grow. And once the whitecaps are forming, this is a dissipative process, and that will stop the growth and will allow us to form a fully developed sea that's not growing any further. Okay, let's see what else we have here. And this is actually all I want to say here, just in terms of the seas, right? So we have basically an area where we generate the waves starting from the ripples, where it just starts to form, and the waves will, as you go through this area of the fetch, they will become larger and larger, and they become a fully developed seas. Once these waves leave the forcing area, then they will propagate as free waves, and they will change to a swell, as we'll discuss in a little bit and when we look at the review dispersion. Okay, so the waves themselves are very influenced by the water depth. That gives us two limiting cases of deep water waves and shallow water waves. So deep water waves, they travel in very deep water, as the name says. And deep water is defined here as water depth that's deeper than half of their wavelengths. So as we just said, the surface gravity waves that you can see when you look out on the ocean have a wavelength of, let's say, a few hundred meters. If they're traveling at 4,000 meters depth, they do not feel the bottom, the ocean bottom, and so they're not affected with the ocean bottom. That has to do with the orbital motions of the water parcels as the wave passes through. These orbital motions are, for the deep water waves, basically circles with an amplitude that decreases exponentially with depth, and decreases exponentially with depth that's related to a fraction of their wavelengths. So again, if the water depth is much larger than the wavelengths, then there will be no motion anymore at the depth associated with the bottom, and there's no, these waves do not feel the ocean bottom. In contrast, if the wavelength is so long that it's in this case that these orbital motions interfere or interact with the bottom, then we have shallow water waves. Definition here is shallow water waves are in water shallower than 5% or 1/20th of the wavelengths. And now we have the propagation of these waves are very strongly influenced by the water depth. We see also that the orbital motions, which were approximately circles, and in the deep water waves, in the shallow water waves, these circles will flatten. And actually, as you go closer to the bottom, there will simply be a back and forth along the bottom. Right, and then the shallow water waves, they occur when the water is shallower than 5% or 1/20th of their wavelength. Now, the speed of these waves, again, depends on their character. So the deep water waves, so the waves that are in waters that are much deeper than their wavelengths, the speed of these waves depends on their wavelengths, such that longer waves travel faster than shorter waves. The speed of the wave is given here by these celerity relationships between the speed of the waves and either the period of the wave or the speed of the wave and the wavelength of the wave. You can see this, and you see this is between C and T. They have different relationships with a period and the wavelengths. And if you look at this relationship with the wavelengths is nonlinear. It's looks like a parabola, or actually like a square root, not like a parabola, like a square root. And you see that overall the speed of the waves increases as the wavelength becomes longer. The speed is higher here than here. And if you look at these numbers here, 1, 2, 3, 4, 5, this is the period in seconds, that the speed of the waves becomes larger as the period of the waves becomes longer. Okay, this is for the deep water waves. If you look for the shallow water waves, now they behave quite differently. Now their speed depends on the water depth. It does not depend anymore on the wavelength or period, but they only depend on the water depth. With this relationship here, where the speed of the wave is proportional to the square root of the depth, actually gravity, g times h or g times t, square root of gravity times t. You don't have to remember these equations, but you should remember which waves, when these waves are faster or slower. So you see that this wave is proportional to the square root of the water depth. So the deeper the water, the faster the waves are propagating. Okay, so note again, for the shallow water waves, we have a dependence on the wavelength of the speed, right? So the longer the wave and the larger the period, the faster the wave. This is for the deep water waves. For the shallow water waves, there's only dependence on the depth. Okay, so if we now look at the wave propagation, there's one aspect that we have that's very important to distinguish. It's the distinction between the phase of the wave, meaning the speed with which a particular high trough or crest or trough of the wave propagates. This is the phase speed of the wave, and the speed with which the whole group of waves propagate. These speeds are not the same for the deep water waves. The group speed is half of the individual wave speeds. So the crests move at twice the speed than this entire group. So the important part of this is that while the speed of the crest tells you again whether a particular crest of the waves, how fast it will approach a particular location. If you're interested, let's say, in when high surf will arrive at the North Shore, then it's not the speed of the crests that's important, but you're interested when this whole package arrives at the North Shore. And the speed of that package is determined by the group speed, as it's called. That will determine when the swell actually arrives from the distant generation region. So this is the speed with which the energy propagates rather than individual crest. And for the deep water waves, that group speed is half of the speed of the individual waves. And you see in this depiction, you see this this package moving from the left to the right. And within this package, a particular crest will actually move at twice the speed through the package, will appear at the back of the package, and they'll move and disappear in the front of the package. Right? So the important thing is that if you're interested in the arrival of waves, then when the wave group arrives, when surface is going to be high, for example, then you have to look at the group speed. You don't look at the phase speed of the waves. Any questions for this so far? Okay. Now this brings us to wave dispersion. We mentioned already that the phase speed of these waves is a function of the wavelength. And remember, again, for these deep water waves, the phase speed is twice the group speed, so that applies both to the phase and the group. So the speed of deep water waves is faster for the longer waves, right? We see this here. So if you now think of a situation where we have the generation of waves in the stormy areas where we develop a fully developed sea that has all kinds of wavelengths. So it has both the superposition of short wavelengths and long wavelengths. They're all bunched together. Now, once they leave the fetch areas, the longer wavelengths as part of this group, they will go faster than the shorter wavelengths. So this fully developed sea will separate by wavelengths. That if you're some distance away from the storm, the longer waves will arrive first and then will be followed by the shorter waves. And so that is responsible for these very clean waves that we see at the North Shore, or generally from the waves from a distant storm, that they will convert from the sea, from the fully developed sea, to a swell, which is nicely separated by wavelengths. And so the longer waves will arrive first compared to the shorter waves. So this is called wave dispersion. So please remember that, again, the longer waves travel faster than the slower waves and give us the separation of a wave package that are all generated at the same time and same space. But as we go away from this generation region, the longer waves will arrive first, longer, and waves with larger period will arrive first, and then the shorter and shorter wavelengths, waves with shorter wavelengths and shorter period will arrive later. Refraction is a very important thing. We said, okay, now these surface waves, deep water waves, as they approach the shore, they change their character from a deeper water wave to a shallow water wave, because simply their wavelengths, the ratio of their wavelengths to the water changes because you're moving into shallow water. And that causes then these waves to behave according to the speed relationship for the long or the shallow water waves, where the speed depends on the depth. And so you see a wave crest that approaches the shore at an angle, where with this part here will encounter the shallower part of the waves earlier than the part that's still in deep water waves. And so this will slow down as compared to the part of the same wave crest that's further offshore. And so that will start to bend the waves as they're approaching the shore. And so the tendency is that the swell will bend towards the shore and will try to become more parallel to the shore. You see that very nicely here, how the swell moves around and then bends, these wave crests bend as they go into the shallow water. It's called wave refraction. That's the process by which waves bend as they go into shallow waters. Now wave breaking. We mentioned that, so we are now closing to the shore. So deep water waves goes into shallow water, and eventually the swell will feel the bottom when the water depth is shallower than 1/2 of its wavelength. And so as a result of it, the period of the wave will be unchanged, but the wavelengths, the wavelengths will change. Will change, and as a result of it, the wave crests become peaked. Right, so all this energy in the deep water waves that's focused into less depth, and so that will increase the amplitude of the waves under the crest will become peaked, and the troughs will become much longer. The waves will become slower because the water depth becomes shallower, and as the waves approach its critical ratio, this critical steepness of 1/7. Between the wavelengths and the wave amplitudes, the waves will start to break in terms of these whitecaps. Again, they start to sort of spill. You get these whitecaps at 1/7. And when the wave height was 3/4 of the water depth, then they actually start to break. This is a process by which we break the waves as we go for deep water waves. As it approaches the shore, its speed becomes a function of the depth. And as a result of this, the wave will become peaky and eventually will break. Now, the number of ways it can break, as you see, it depends on the way the topography or the ocean bottom slopes. If the bottom slopes very gently, then these waves will peak and eventually they will break and have sort of these spilling breakers. Just as they just spill over. If the ocean bottom is quite a bit steeper, then actually, since the speed depends on the waves, on the speed of these waves will depend on the water depth. You see that the crest has a larger water depth, and so it moves faster. And actually, if it's steep enough, it will increase its speed so fast that the waves will actually plunge and make these nice barrels that you know and love when we watch surf or when we do surf. And if the bottom of the wave is too steep, then the wave will simply surge up and down the beach. So the types of breaking waves will depends on the steepness of the bottom slopes. And we have these three types of primary breaking waves: the spilling, the plunging, and the surging. And if you go along the beach in Waikiki or go to Makapu Point, you can see these different characters of Waikiki. There's a lot of spilling breakers. If you go to Sandy Beach, you have these plunging breakers, the extreme version of it. And sometimes you see the surging breakers and the Sandy Beach as well, where simply the water rushes up the beach. Okay, so we just went through this, surging breakers. We just went through this. Any questions regarding the waves so far? Okay, well, I'm just really burning up the time here. Tsunamis, very important. So tsunamis are, of course, extremely destructive. They are very long wave, progressive waves. They are caused by rapid displacements of large volumes of water. Typically causes earthquakes, landslides or undersea landslides, iceberg carving, volcanic eruptions, asteroid impacts is a possibility. These are shallow water waves, and they are shallow water even in very deep ocean water of 4 kilometers depth because their wavelength is so long. Their wavelength is 200 kilometers or more, so this is the wavelength is much larger than the water depth, and so they are shallow water waves. The speed, therefore, depends on the square root of the depth. And so just to give you an appreciation of the speed here, so for 4 kilometer water depth, their speed is 720 kilometers an hour, 450 miles per hour. That's the speed of a jet. So these waves propagate through the ocean in deep water with the speed of a jetliner. As these waves in deep water, these waves have, again, there's shallow water waves, propagate very fast, but the amplitude is rather modest, maybe half a meter. They're very gently sloped because you have such a long wavelength. So with the boat out here, you won't even notice them passing. But as they go into shallow water, all this movement of these deep water waves that extends throughout the water column is focused more and more into shallower depths. And so their amplitude becomes stronger and stronger, larger and larger, right? And so that's because, again, this volume that they displace is large. And as they approach the shore in the shallow depth, these wavelengths become shorter and the height becomes much larger while the period remains the same. And this is a picture of the Indonesian tsunami, where we had first a trough arriving and people went out and checked out the tide pools, and then the wave came. Periods of these waves are typically of the order of tens of minutes, 20 minutes. So be very wary when you see the water recede on the shore, and don't go out, check it out. Would quite the contrary, go to higher ground because that might indicate a tsunami. Okay, that's tsunamis. Again, this is very important, these sort of things. Maybe that's not on the test, but you should really know this. This is just living in Hawaii where we are subject to tsunamis. You should know what to do in case of a tsunami in terms of evacuating to higher ground. Particularly if you're taking classes like oceanography, you have a leg up to many other people, to many of your friends and family. And so they might look at you for guidance, what to do if the sirens go off. So you tell them, just evacuate to higher ground. Don't check out things because they look so interesting. Okay, the final topic that we had were tides. So the very important part of the tides is the tide-producing forces. Tides are produced by an imbalance, or by the combined Earth-Moon or Earth-Moon-Sun system. Let's just focus on the Earth-Moon system. This system this rotates around a point within the Earth. As a result of this, over the course of a month, this thing rotates around this point somewhere 1,000 miles from the surface of the Earth. As a result of this, all points on the Earth experience the same radial acceleration, the same centrifugal force. So you have these red colors, the inertial forces are always the same. However, the gravitational forces indicated by these blue arrows here, they depend on the distance between the Earth and the Moon. And of course, for the Earth's center, these inertial forces and the gravitational force exactly balance, but at the surface of the Earth, they do not balance. As I said, the inertial forces are the same everywhere on the Earth, but the gravitational attraction is stronger when we are closer to the moon, and it's weaker for these points that are further away from the moon. As a result, there's these, if you add up these two forces, you get a residual force, which is, again, in the phase towards the moon, goes towards the moon, on the opposite side on the Earth, faces away from the moon. And the most important thing, it has a horizontal component away from this point, but it's exactly perpendicular to the surface of the Earth. And that will cause a tidal bulge, or will accelerate or force a tidal bulge that's closer to the moon because of the gravity is larger than inertial forces on the side of the Earth that's towards the moon. And the gravity is smaller than inertial forces on the side of the Earth that's away from the moon. So we'll generate, because of this balance between inertial and the gravitational forces, we'll have two tidal bulges towards the moon and on the opposite side of the moon because of these differences in the balance between the gravity and inertial forces. Now, let's see, we just had this. Now that brings us to the equilibrium tidal theory, very important. That explains a lot of the aspects of the tides that we observe, but not everything. And so you see, this is now a situation of the Earth where we look at the Earth from the North Pole. And you see that we have the moon. We have a bulge of the moon on one side on the side of the Earth towards the moon, and the other bulge on the side away from the moon. And you see that would produce, if the Earth rotates in 24 hours around its own axis, then you would generate certainly two bulges, two high tides and two low tides in the course of a day. But the period is not exactly a day, because in the course of the day, the moon also moves. And so these semidiurnal tides, so it's two tidal ridges, two highs and two lows in the course of the day. These don't have a period of 24 hours, but they have a period of 24 hours and 50 minutes, because in one day, the Earth moves 1/27th of 360 degrees, which corresponds to 50 minutes. Right, so that's very important. So this equilibrium tidal theory predicts us two tidal bulges. The tidal bulges may be, if the moon is not in the equatorial plane, the tidal bulge at a particular location may be high and low. Right, there might be high and a low high, as you see already, because the tidal bulge is not in the moon is not in the equatorial plane, but off it. So it generates quite a nice. Explains both two tidal bulges in the day and two highs and two lows. Explains that the period is not exactly 24 hours, but 24 hours and 50 minutes. And also can explain that there may be a higher high and a lower high. Now, it's not just the moon that affects the system, but also the sun. So even though the sun is much further away, it's much heavier, such that the influence of the sun on the tides is about 40%, 50%, about half of the moon. So we have this entire equilibrium tides, we have them both to the moon and the sun. If the moon and the sun are aligned, which happens either at the new moon or the full moon, then these tidal bulges add up. And we have particularly high tides, which are called the spring tides. So that happens since the moon goes around the Earth once a month, in about a month. So that happens twice a month when we have spring tides. And when the sun and the Earth are at 9 degrees to each other, so that's now the first quarter moon or the three-quarter moon. Now these bulges, they don't add, but they are superimposing such that we make this solar bulge. The solar bulge is associated with the low of the moon, and and opposite, that the moon bulge is associated with a low sea level associated with the sun. So they are subtracted from each other, and we have much smaller tidal ranges, and these are associated with times of the moon in the month when we have either first quarter or third quarter moon. Okay, So that's about the tides. This is equilibrium tides. So it explains very nicely that we have tide producing forces at an annual period, at the diurnal period, in a semi-diurnal period, and a diurnal period, and explains very nicely the spring neap cycle of the tides. Now, the real tides don't behave quite, they are forced at these periods that we just said. So they are forced by the tide producing forces at the diurnal and semi-diurnal periods. They are forced by the modulation of them over the course of the month in terms of the spring neap cycle. But of course, for the equilibrium Earth, we're assuming that the Earth is covered by very deep borders everywhere. There are no continents, but of course there are continents. And so the tides actually behave like waves that bounce around the ocean, being produced by the tide producing forces, but they don't follow this very simple equilibrium tidal model. And we can represent these motions by this dynamical tides, how they actually occur in the deep in the Earth's oceans. And represent this for a particular period. Let's say this is semi-diurnal period. Actually, I'm not sure what this is. We can show this by these co-tidal plots. They show two things. They show in color the amplitude of the tides. So where the tides have a very large amplitude, where there's small amplitudes, these hot colors being large, these bluish and white colors being slow points, bluish colors being low amplitude. And they show the phase. These white lines are the phase. So these points on one line will experience a high or low tide at exactly the same time. So the high tide will arrive at the same time here as it's arriving at this point. Okay, and you see that this is arranged in these sort of circular fashions. These waves move around these points, amplitudinal points, where the amplitude is zero and all the phase lines come together. They move around in a circular fashion. The tidal range obviously is a minimum or zero and the apogee points, and tends to increase outward, radially outward. Let's see. Right, and so these dynamic tidal theories, they predict sort of three types of dynamic regimes. So we have either semi-diurnal tides. These are areas where we have two high tides and two low tides every day. We have other places where we only have diurnal tides. So we only have one high tide every day and one low tide every day. And then there are areas where we have mixed tides, where we have, again, two high tides, two low tides, but they have very different amplitudes. So we have a high and a low high and a low low and a high low in terms of their tidal ranges. And this is an example here, is just shown here. In terms of semi-diurnal, it's all the same. Diurnal, only the diurnal period. And here we have the mix between the higher high tide and the lower high tide and so on. And I think that's all. Just tidal prediction. We can, tidal predictions are very important that typically in the open ocean tides, we have the strongest tidal. The flood tide is the currents that go from low to high tide. Net tides are from high to low tide. The currents are strongest when we are just in the mid-water. The currents are weakest when we are in slack water, when the tide is either highest and lowest point. And I think that's all I have here. Predictions, of course, of the tides. You see this. We can predict the tides very well because they're produced by the astronomical forcing. And you see that the blue one is a prediction. We can predict that years in the future. And the red one is actual tidal range. You see the variations are very nicely aligned with our predictions. There's an offset because there are other things affecting sea level. And I think that's all I have. I used up all the time. Any quick questions? How many questions are on the exam? The exam is always, there's a multiple choice part of it. Then there's a fill in the blank part of it. And what was the third part? Multiple choice, fill in the blank, yeah. So there were 30 questions. Should be able to do that in no time. Typically, people finish the exams in much less time than we have allotted. Any other questions? Okay, if not, well, then thank you very much for stopping by. Good luck on Friday. I see you in either the 10:30 or the 12:30 session. Again, don't forget it's in the Biomed building, right? Same place as we had the last exam. Okay, bye-bye.